Welcome back to the Primary Science Podcast. Today, we're continuing our mini-series on inquiry-based learning. To help us unpack this, I'm joined by Tracy Tyrrell. She's a fellow of the Primary Science Teaching Trust, a Primary Science Quality Mark Hub Leader, and a Primary Science Capital Trainer. She's also the author of one of the most useful resources on offer, Primary Science Skills and How to Teach Them, which is linked in the description. So as you can imagine, Tracy has a wealth of experience and knowledge in teaching primary science. And today we're going to be focusing on practical strategies to help build those inquiry skills. So whether you're just starting to explore inquiry-based learning or looking for new strategies to improve your approach, just stay tuned. Okay. So, Tracy, welcome to the show. It's actually a really wonderful treat and a privilege to have you here with us today. It's not every day that you get to speak to someone with as much knowledge and experience as yourself. So welcome, and how's everything going?
Thank you. Thank you for having me. Thank you for asking me. Yeah, everything's good.
So I'm actually really intrigued to learn more about how you got to where you are today, though. And I just wonder if you could tell us all a little bit about your journey into teaching and science education in general.
Okay, so my love of science came first. I had a really fab secondary school biology teacher who really got me into science. I loved her lessons. I wanted to learn more. Unfortunately, I didn't go on to further education after school, but I started to work at a local research lab, Unilever Research, in a village nearby, working in the lab, growing and testing monoclonal antibodies, but also they did a fab scheme there where you could take your qualifications day release whilst you worked there. So I did that. I did a HND in biochemistry and then a degree in biochemistry. But by then, I'd had my children. Research science is a little dull as well. You're sort of doing the same thing over and over and over again. So I thought I'd have a change of direction. And teaching really wasn't something I'd thought of before, but having young children, I thought that would fit in nicely with, the holidays and things. So that's what made me change direction at 30 years old. So I left the lab and went back to university, studying whilst at home with young children. That was a bit hard, and I had my third child whilst I was working towards my degree, and then I qualified in 2001. Been a primary science teacher since, science subject lead for most of that time because of my background. The primary science community is so generous. There's such a fab wealth of resources out there, advice online and in person. I came out of the classroom, it must be two years ago now, to focus on teacher training, writing resources and bits and bobs like that.
Lovely. And now you kind of wear many hats, don't you? I guess.
Yes, I'm a primary science quality mark hub leader. Have been for 5 years, so I help other schools work towards improving science teaching and learning provision in their school so they can gain a primary science quality mark. I do things for the Primary Science Teaching Trust because I'm a fellow of the Primary Science Teaching Trust. Get all sorts of opportunities through that, and through the Primary Science Teaching Trust, I've become an accredited trainer for Primary Science Capital Teaching Approach, which is, in my opinion, the thing that has made the most impact on children in class. It's a fab approach, and if you haven't looked at it, I thoroughly recommend you do so. I've got to write resources, got to write blogs for online engineering companies. Yeah, so lots of different things. Oh, and
That's
I'm
amazing.
a facilitator for STEM learning too. So I do some in-person training at the York STEM Centre, but also online training for teachers too.
Wow, that's amazing. You do so much for the community, and it's actually really interesting to think that you and I have similar backgrounds. So I I started off in science as well. I did a degree in biochemistry at Leeds. And then I went on to do my doctorate degree, and I was developing biosensor technology using antibodies with Unilever. And actually, one day, I would really love to go on and do something similar to yourself and perhaps work in anything to do with the primary science community, because it is such a fantastic community, as I'm
It is.
very quickly learning through these podcasts. So it's now time for one of my favorite parts of the show, because it gives a bit of a unique insight into the guest. So it's the quickfire five. So I'm going to ask 5 questions just to help us all get to know you a little bit better. Are you feeling ready?
Yep, ready.
Very good. Okay, so question 1. What's your favorite science resource to use in the classroom?
It has to be Explorify. It's an online resource library. Have you heard of it?
I have, yeah, I've used Explorify as well. Yeah, got it as a tab on my computer.
It's such a fantastic resource. It's free, it's quick, short, sharp activities, range of activities. It could be odd one out, big question, have you ever, all really fantastically illustrated with either photos or videos. And it gets children thinking creatively, it gets children discussing. Most of them, there's no right or wrong answer, so every child in the class can have something to say. There's really good teacher's notes to go with it, every activity to help you run the activity to the best advantage. It's all linked to the science curriculum, probably UK curriculum, but the concepts are worldwide, aren't they? And children just get to discuss, explore, and think laterally. And you, whilst they're talking, can sort of figure out what they understand, any misconceptions they have that you need to correct. It's just a fantastic tool. Fantastic.
Yeah, I have to second that for sure. And I could definitely be using it a lot more in the classroom as well.
It's ever expanding as well, because although it was originally created by Louise Stubberfield and the PSTT, Primary Science Teaching Trust, and ASE are now curators, and they're developing new activities all the time. Fab one is Have You Ever? They're the new Science Capital activities that sort of root children's learning, science learning in their own experiences. So you start the lesson with Have You Ever? And it could be Have you ever tried to turn something on when it's not plugged in, and it sort of takes you to switches? Or have you ever seen a plant grown in an unusual place, and takes you to seed dispersal? But it sort of hangs the children's learning on their own experiences and relates it to their real lives. Really good set within Explorify.
Very nice. Okay, question 2. What's a common misconception about teaching science?
I think a lot of people and children think that science is all about awe and wonder and making children go wow, or should be about awe and wonder and making children go well. Secondary schools are awful for this, by the way. Every time year 6 go off to the open days, it's like, oh, we saw Bunsen burners and chemicals and things. And I think there's a lot of science that does make children go wow. However, it shouldn't be that shouldn't be the aim. It's about, learning the concepts in the best way ever. I've been and spoken to children and said, oh, what's been your favourite science lesson in different schools? And they've been able to tell me about this fantastic activity they did, exactly what they did, but not why they did it and the science behind it. So yeah, we had the bottle of Coke and we put the Mentos in and it all exploded, but not relate it to the science learning and the fact that it's irreversible changes they were looking at. They just remember the activity. So, yeah, I think focusing on the learning first and then finding an activity that will promote that learning rather than focusing on an exciting activity.
Yeah, absolutely. And question 3. What's your favorite science topic to teach?
I'm not sure this will be everybody's favourite, but I love evolution and inheritance. I love
Okay.
it's just exploring camouflage and other adaptations in plants and animals, not just the exotic ones. The go-to is a polar bear and a camel, but the weeds in the average school playground, the brambles, the dandelions, and things like that, are just have fantastic adaptations as well. I love exploring the timeline of Earth with children. Getting rid of their notion that dinosaurs and humans were around at the same time, and showing them just, in the relative scheme of things, how short a time humans have been on the earth. And I love looking at inheritance, helping children look at what they've inherited from their parents, but also looking at other animals. It's just a fab way of understanding what a brilliant diverse range of living things we've got on our planet and why they're like that. There's some really good storybooks you can share too. There's The Moth by Isabel Thomas and The Mollybird by Jules Pottle, both about adaptation and inheritance. Really good storybooks.
Yeah, you make a good point there, because I think quite often evolution and inheritance is seen as quite an abstract concept to teach. But actually, that's where all the big questions that the kids really want to know lies. So yeah, I really find that interesting that that's your favorite one to teach, and I like your take on it there. So, okay, question 4. Who's your science hero or your inspiration?
It has to be Anne Goldsworthy, has to be. When I first qualified in 2001, my very first science subject lead network meeting, there was this fab newish resource that Anne Goldsworthy had written, Developing Understanding of Science Inquiry. And it's all about teaching inquiry skills. And it was fab, and I loved it. And then I looked out for more of her stuff, science inquiry games, primary science toolkit. But also, I looked out for presentations she was doing. Kind of ended up stalking her in a good way, because she's just such an inspirational speaker. Her advice and her tips and her things she recommends are just so focused, cut to the problem, cut to the issue. Really helpful, really useful, really practical ideas she gives. So yeah, she's been my primary science hero throughout my time in school. However, I got to meet her and work with her a few years ago. This initial book that made me aware of Anne Goldsworthy, The Developing Understanding of Primary Inquiry, another fan of this resource, the director of the Primary Science Teaching Trust, wanted it updating, rewriting for the sort of current curriculum. Also, it was written for a strange age group. It was written for 9 to 13-year-olds, which sort of cross phase in the UK. And I got to rewrite this resource. I just finished it a few months ago. And all that time, Anne has helped me. Anne has read everything. She's advised. She's encouraged. She's been such an awesome help with it all. So generous with her time and her experience. Yeah, she's just, my hero.
Yeah, and that's just a testament as well to, again, how great the primary science community is, and how, Anne has made an impact on you, and then you can go on and make an impact on so many other people. And you mentioned a resource there, the book that you've written, and that Anne helped you with. Is that something that we could put as a link in the description where listeners could go and find it?
Yeah, and it's free for ASE members. So if you're a member of the Association for Science Education, I'm not sure whether that's an international thing or just a national thing.
Yes, yeah, I looked into it the other day, and I'll be becoming a member very soon.
Yeah, and it's all free on there, but otherwise you can buy it. Okay.
Brilliant. Okay, and the 5th and final question. What's the most exciting discovery that you've made in science, but with your students?
Well, it's all about the power of the mind, actually. When I was in school, we used to run themed weeks, science and another subject week. We did a science and PE week. And there was lots of looking at health and exercise, heart, forces and sports. But we also ran an investigation in year 6 into sports drinks and whether they actually help people run faster. So they researched what were the general ingredients of the everyday sports drink, the isotonic sports drink, and they created their own. And then they ran this investigation with 3 large groups of children, 3 large classes of children, where they gave one water and asked them to run a certain distance and took the sort of timings and averages. And then they gave one their sports drink they'd developed based on their research, and then they gave one coloured water, which was sort of described as a sports drink. And if the sports drink had had an effect, you'd think it would just be the sports drink that made children run faster, but actually the coloured water did as well. So it was a mind experiment. They thought they were going to run faster because of what they'd just drunk. They did. It wasn't anything to do with the drink.
That's really interesting. And I bet, you see, it's the lessons like that that stick with the kids the most, isn't it? I bet that all of those students still remember that.
Yeah, probably.
To this day. Yeah. Oh, that's really good. Okay. That's the end of the Quickfire 5. Okay, so it's really good to get to know you a bit better there. But I think now it's time to get to the heart of today's topic. So that's about helping students to build that science inquiry toolkit in themselves and become more independent scientists. So to start us off, what does building that science inquiry toolkit in students really mean to you?
Well, the toolkit is going to help children work like scientists. And it means teaching explicitly inquiry skills across primary school, right from early years where you're teaching children how to observe carefully and ask some questions and things right through, so that in year 6, the children can confidently ask a question, decide how to answer that question, decide what's the best way to answer the question, make really good planning decisions, make accurate measurements, observations, record it, present it, describe it, evaluate it, and do that, get useful results and be able to do this all independently. So the toolkit really is based on teaching skills throughout each year group, building on those skills. So by years 5 and 6, they're confident scientists.
Right. Okay. So it's more, rather than just feeding them the skills, it's like teaching them how to use the skills.
Yeah,
kind of
teaching
like the
them
analogy.
how to. Yeah, Paul said about it in the last podcast. Focused teacher input, explicit teaching at the beginning of a lesson, getting them to explore something, and then discussing what they've explored and pulling out the key teaching points, then they can apply it to their own inquiry and the rest of the lesson. It's a bit like English. You get you craft children's writing by teaching them the aspects of grammar. You might teach them fronted adverbials at the start of the lesson and then expect them to include it in the writing. And you wouldn't expect children to get better at writing just by carrying on writing more and more and more. You have to teach them the skills. So same with science.
And as teachers, I guess kind of like the next logical step here is sort of how could we do that? Like, are there some specific strategies for teachers to kind of foster that independence and build up those skills in the students?
Well, I mean, Paul touched on it again in the last podcast. He said about how he would teach online research skills. He'd give children something to explore, whether it be find an image, find the answer to a question, let them get on with it, and then pull them together to discuss, any issues, any problems, how they could refine the skills. So in this case, it might be what they actually put into the search bar. And it's the same could be the same for any skill. Just giving children something to explore together, a lot of discussion, in pairs or small groups, then pulling them together as a class and discussing any issues, what they thought, So, for example, observations over time. Observations over time are done right from early years year one, where they look at changes in the season, right up to year 6, where they're looking at how a shadow changes over the day, their shadow changes over the day. A key skill there is deciding how frequently to observe or measure and over what time frame. So you could give children a variety of scenarios, perhaps how the temperature changes of a kettle as it boils, how a bean changes as it germinates, and give them some multiple choice options. Should we observe or measure this every second, every minute, every week, day, every week, and give them several options? And then what sort of time frame? Should we do it for 10 minutes? Should we do it for a day? Should we do it for a week? Should we do it for a whole year? And they sort of circle the best options for each scenario. They could also circle the worst options for each scenario. And then when they've done that together as a group, you pull them together, discuss what they think. And actually, the talking about the worst scenarios is the most valuable, because then you say, why? Why is that? Why would that not be useful? And they can think then about, actually, if you do the wrong frequency, the wrong time frame, you could miss important changes. It wouldn't be worth doing. Or you could waste a lot of time just hanging around and nothing happening. And they're the key things that they need to decide on when they're planning their own observation over time. What would get the most useful results? We have to see these changes, but also what would be the most time efficient. So that's a good teaching point for that one. You can get sketching. So quite often, I think children think that drawing a bar chart or a line graph at the end of an investigation is like illustrating a story. It's like the decorative bit, rather than seeing that as telling the story of the results. So you could give them a scenario. Again, lots of these involve scenarios. So we've got a cup of warm water, beaker of warm water sitting on a desk with a thermometer in. How do you think the temperature is going to change from when we place it on the desk to 24 hours later, and ask them to sketch the line they think would represent that happening? They have to think about where the line would start, the gradient of the line, how the line would change, where it would end up, and all that discussion helps them to really get into interpreting what a line might show. And they'd be able to then put those skills to better use when they're producing their own line graph. They'd be able to write about the graph or chart that they've created. There's quite a few different ways. Matching is a good one. So pattern seeking, that's quite tricky. Talking about links. Is there a link between leg length and distance jumped? Is there a link between the length of a sycamore seed and how far it goes from the tree? And actually the scatter graphs produced by investigations like that are quite tricky for children to understand. So you could give them some example scatter graphs, one that shows a good positive correlation, one that shows a good negative one that shows no correlation at all, and get them to match the description of the scatter graph to the correct scatter graph. And I think evaluation and ranking is always a good one too. So when it comes to describing your results, explaining your results, in English we always used to give children waggles, what a good one looks like. And this evaluating or ranking is a way of giving children what a good one looks like. Again, you give them a scenario, a simple one. By the way, there's a key point here. All these scenarios that you give them should be simple or familiar. Just like Paul said, he'd do something that the children could really understand when doing online research, not specifically science. I think with other skills, it probably does have to be a science context, but it should be familiar to the children. So it's just the skill they're working on, not trying to unpick the science understanding. So, so you give them a scenario. It could be the sound produced with different thicknesses of elastic bands. And you give them some examples of children's descriptions of the results. And these could be fictional that you've made up, or they could be pulled from previous years or other classes, and ask them to look at which is the best description and why, which is the worst description and why. Can you rank these descriptions, and then again, once they've done that in small groups or pairs, pull them together and talk through. The descriptions need to be carefully chosen. So it has to be really bad examples. Bad examples of descriptions are vague. So they'll say, the biggest one was the best, or it was different when we pinged the wider band. They don't really say anything. Or you could get the descriptions that just focus on one result. So when the thinnest band produced the highest sound. But then good examples as well, the waggles, which say the wider the elastic band, the lower the sound produced. And get them to look and examine them, find the best one, find the worst one, discuss those, and while you're discussing those key teaching points can be pulled out. A good description doesn't use vague words like the best. It describes all the results, not just one.
Yeah.
So that's another way. But what it is mainly is giving children some example of what you want them to do, some example to examine and comment on and explore, and then discuss and pull out their key teaching points.
I'm just soaking it all in at the moment, and it's really interesting because as I'm listening to all these really wonderful examples and practical things that we could do, I can't help but think that we almost need this to be a dedicated time on the timetable each week, So
I don't think so. I think if you are doing an investigation, it just needs to be that, these are all quick activities. It's not like a whole lesson. It should be sort of like 15, 20 minutes at the most, probably some even 10. The multiple choice on the observations over time, very quick. Sketch the line, very quick. Some are a bit more involved, but yeah, just every practical lesson, every inquiry lesson, should have a skills focus. And that's the skill you're going to give the teacher input in. And then when they go on to apply it to their own investigation, that's the skill they record, that's the skill you assess. Yeah, so it makes it quite easy for the teacher. The rest could be done as a group. Yeah, so I think it's good as a pre-investigation starter.
Yeah, I was going to say, so it's almost like as a school. So say if you were trying to implement this in a school as a whole, you would need to almost have a bank of different ideas and then include that as part of the planning.
It's funny you should say that. There's a book I know.
Nice. I was hoping you were going to say that. Yes, tell us.
Oh, well, it's called Primary Science Skills and How to Teach Them, or PSHT, as it's known in the primary science teaching circles.
I love that.
Yeah. So there is a bank of these ideas in there.
Perfect. So is that a resource that you've written?
Yes. It's the rewrite of Anne Goldsworthy's Developing Understanding in Science Inquiry. And it's free for all ASE members. I'm not promoting it to make any money. I do not get any money. It's free to ASE members. And membership for the Association for Science Education has just gone down to, I think it's £42 for the year. Well worth the money.
Yeah, that sounds about right. Yeah. Okay, so that's the book that we're going to put the link to in the description, right? So perfect. So everyone can have a look at that bank of ideas. And then I guess going back to what I was saying, I think it would be great for teachers to then develop that as a habit. So every time you have a science lesson as part of your starter in the planning, or however you set up your lessons, to then use an appropriate one. But I mean, how appropriate does it have to be? Is it more the skill that needs to be the one they're using, or does it need to be directly related in terms of concept?
I think at the moment we're in the UK. We're very good at planning for progression in knowledge, in the concepts, in conceptual understanding. We're not so great at planning for progression in the skills, working scientifically skills. So at the moment here, I think it's, if teachers notice a gap in the skills, a real gap, or they know they haven't even looked at evaluating any investigations at all, they could choose one for their class. But in the long term, really, there needs to be planned progression across the whole school, so that they know in early years, year one, they're going to develop this skill, and then move on to this in year two, and build on these skills across the school. I mean, it could be the same resource. So, for example, the sticky note planning. Have you heard of the sticky note planning? I know
I
that
have,
Andy
yes.
Goldsworthy resource. So that's usually introduced in year three because it's to do with fair testing and comparative testing, but it is fair test. And it's a fab resource. And still a large proportion of inquiries in primary school are fair or comparative tests. And this strategy guides children through the whole process. If you introduce it in year three as a guided process, first of all, in the autumn term, perhaps even in the spring term, you're going through it together. You let them explore, I don't know, magnets and picking up paper clips, and you think, I wonder what makes a difference to how many paper clips a magnet can pick up, and get their ideas. So after, the exploration is key as well. You can't just ask them that question without having a play. And they'll come up with all sorts of ideas. It might be the size, it might be the shape, it might be, different things about the magnet, or, paper spinners. What might affect how long it takes for a paper spinner to fall to the ground? And they could come up with the material it's made of, the wing length, and things like that. You record all those in that uncoloured sticky note. Then how are we going to measure the effect change in one of those things has? So we'll measure the time taken to fall. And this starts as a guided process in year three. You can go together and choose one thing to change. So we'll choose the material. Okay, so it's going to be a comparative test because this is a discrete variable. It's described in words. So we're going to do a comparative test. We're going to change the material. So how does the material affect the time taken for the spinner to fall? All could be done together with the children, and you plan it together. And the sticky note planning takes you right the way through to recording in a table, making a prediction, all sorts. Then you can gradually take that support away. So perhaps by the end of year three, you're asking them to have an explore, but then think about all the things that might affect whatever it is they're exploring by themselves, and then gather those together and make sure you've got a good list and everybody knows all of the things people have thought about. Then the next time you might get them to create their question. Right, we've generated this list of things that might affect X. Can you create your question by changing one of those? And they say, how does this thing they're changing affect? And gradually focus on one area of that until year six. I've had it where year six have just, usually the teachers have their fair test, it's written down, they know what they're going to do, they know all the resources they'll need, they know what the result's going to be. In year six, if they're confident with this strategy, they can, all the groups can be doing a completely different investigation. It does make it a bit tricky for the teacher. It means you sort of have to plan it beforehand and then do the investigation at a later stage, perhaps. Yeah, and completely confidently planning a fair test that will get useful results and understand why too.
Yeah. Have you got any, just like as a celebratory moment, have you got any examples of, students or classes where you've seen those skills really successfully develop throughout the school, and are there any of those standout moments that, we as teachers could look for and that you've seen firsthand?
So I think one time we were looking at decay, how things decay and break down food. And we were looking at ways to stop it. We'd looked at how freezing, how cooking, how salting can stop this, and then we were going to try and find a different way of preserving food or slowing down the decay process. So we'd looked at different examples of how food might be preserved, and we were thinking about how, if we could find a different way, and what might affect how quickly or slowly some pieces of fruit decayed. And they used the sticky note planning to come up with all sorts of things. They thought about the temperature. They thought about whether air could get to the fruit. They thought about additives that you could put in to preserve them. A group of Year 6 boys, they were cheeky chappies, and they thought, oh, well, I know urine contains acid and we have pickles and things in vinegar, and so I wonder if urine would slow down the decay of fruit. Really good way to preserve fruit.
Logical.
Yeah, but it was their idea, and actually I was quite intrigued to see what would happen, as were the rest of the class. We did have to get parental permission. We did have to get the head's permission that they could nip into the toilet to get the sample to put on the fruit. But it just let them go where they wanted to. It was a good suggestion, and I did, perhaps not for the future of food preservation, but scientifically it was a good suggestion, and I was really intrigued at what would happen. It actually broke the fruit down quite quickly.
Okay, right.
Yeah.
Okay, mental note.
Yeah. Just the fact that the whole class is doing completely different investigations, that's just amazing. By Year 6, they can set up an investigation, a fair test or a comparative test or whatever, completely by themselves and get useful results. Excellent.
Yeah, that's a real win, really. And actually, with your example with the group that decided to use urine, I think that was actually a brave choice. The fact that they were able to think of that and it had a logical reason behind it, a scientific reason behind it, and they felt confident enough to go ahead with that. I think actually that's brilliant, because you can't make scientific discoveries without doing something different, or
No, outside the box.
being afraid to think outside the box. So that's a definite win.
Yeah. Perhaps not for the food industry, but
True. Okay. So when I think about teaching inquiry, and especially when trying to give the students independence with anything really in the classroom, and it's something I always have trouble with myself, is finding that balance between giving the guidance that they need and doing the teaching part, but also letting them build that independence. So I think I just wanted to see what your advice was there in this context. Is there any key for teachers to balance supporting their students and still, giving them freedom to do things on their own?
I think it's what we've said before. They need to be taught the skills to be able to do that. I mean, children could independently investigate from the off. Whether they would get useful results, whether they'd find anything out, is questionable. So to be able to independently do inquiry and actually it be meaningful and they learn something, get useful results, that needs the focus skills input. That needs the regular teacher input, and then that is the part they could do independently. I mean, there's ways to help children be independent from the start. So giving them the structures in early years. There's a brilliant tool called I See, I Notice, I Wonder, and that helps them to sort of. I mean, they could look at something like a pumpkin, and the structure that I see. What do you see? And it could be just the general. I see something orange and round. It depends if they know what a pumpkin is, but it could just be their first sort of perceptions. And I notice look more closely. What do you notice? And they might notice that the outer skin is a bit knobbly. They might notice that on the top there's a green sort of stalky bit. They might not know the word stalk, and they look more closely. And then, what do you wonder? And ask them. You've looked at this carefully. Is there anything you're wondering about it? And get them to start asking questions. And finding out the answers is the hardest part, and they do need to understand how scientists work and learn how scientists work to do that independently.
So I guess it's about implicitly teaching the skills first, and then and doing that more so for the maybe key stage 1 or for the younger children, and then as they move up the school, you give them more and more opportunities to use those skills, and you build on those skills. Yeah, providing them with the opportunities to ask the questions and use the skills that you've implicitly taught them. Brilliant. Okay.
That's where the planned progression needs to come in as well, though, because that needs to be, it can't be ad hoc. It can't be, well, I taught this skill today, and there needs to be a long-term map put in place.
Yeah, and actually I wanted to clarify as well. So with the planned progression, there's a range of skills that we want them to have by year 6, right? Would you advise that we add into that planned progression that they learn all of the skills in part from the earliest point, or do you focus on one of the skills in year 1 and then say move on to another one in year 2, if you see what I mean?
I think it'd have to be all of the skills in part. Well, there's less skills in Key Stage 1 anyway. But yeah, all of the skills they should be able to do by the end of Key Stage 1 in part, and then build on them year on year, coming back to them, revising them, practicing them, building on them.
Yeah, okay. And is that, I guess that's the same in every school. So is there almost a standard progression plan, or is that something each school needs to just make themselves?
I think, the national curriculum is not very helpful concerning the work in scientific skills, because the skills are grouped in the UK, the skills are grouped in phases. So Key Stage 1, the same skills listed for years 1 and 2. The same skills are listed for years 3 and 4. The same skills are listed for years 5 and 6. So the progression between year 1 and 2, year 3 and 4 is down to the school to sort of think about it. You can't be too prescriptive, because each school has its own context. Each school has its own challenges. So there might be mixed age groups where they don't follow the national curriculum year by year. So, and there's some topics that lend themselves to different inquiry types and different skills. So it would have to be what suited the school, as long as by the end of Key Stage 1, these skills were in place. Maths is another good sort of tool to help with the progression as well, because a lot of the measuring and the recording and presenting data aligns with the maths curriculum. So that could be built in alongside with a maths subject, get together and see where children should be able to draw their own table or create their own bar graph. There are some mismatches. Science expects children to do a lot more than maths expects children to do. So some of those math skills won't be covered in maths lessons that they need to be taught explicitly to.
And so finally, I kind of wanted to almost create a bit of an FAQ section here by identifying a couple of common challenges that maybe you've seen teachers face when trying to implement inquiry-based learning like this, and maybe how these could be overcome just in general.
Okay, so there's always a subject as a teacher that you think, ooh, I don't really know what I'm doing. I don't really enjoy teaching it. For me, it was music because I'm not very musical. And for some people, it's science, isn't it? So these are the teachers that will like the fact that they know which investigation they're doing for each topic, and they know what resources they need and what sort of results they can expect. And these teachers might be quite wary about moving out of their comfort zone and giving children independence, because there's the issue of, where's this going to go? They might ask things that I don't know the answer to. Results might appear that I wasn't expecting and I can't explain. And I think the best advice in that scenario is just to say, I don't know. How can we find out together? Or, I wasn't expecting that. I wonder why that happened. Let's see if we can try and find out. Because I think the biggest barrier to some children sitting in the class, and probably these teachers when they were children, where they think that science is this big body of facts that needs to be learned. It's all for clever people who are really good at speaking and writing and maths. And actually, if you focus on the skills, it's for everybody. And these children need to be given the chance to show they can really observe carefully, and they can describe their results. It doesn't have to be a writing. And they need to see that it's not a just set of facts to be learned. And actually, it's all about the process. It's about asking questions, answering questions. In that way, more children can be involved. More children would feel as though they're sciencey, would not sit there thinking, oh, this is not for me, this can't do science. And the best way teachers can do that is just to say, I don't know. Let's try and find out. Or how could we find out? I think that's the biggest favour a teacher could do a class of children in science.
Yeah. So you're talking about mindset, I guess. Yeah.
And I think the other thing that perhaps would be a barrier is the resourcing, the noise, the activity, who's doing what. Resourcing is quite easily. Science ambassadors are fab. In appointing some children to be science ambassadors and be in charge of resourcing and getting things out and putting things away, because it is a faff, isn't it? It's easier to pick up a worksheet than go rummaging around trying to find this, that and the other for inquiry lessons. So yeah, science ambassadors totally recommend to save some of that hassle. And they love a bit of responsibility. And group roles is another good. Explorify is a way of getting children to realise that everybody can have something to say, and really creating that inclusive atmosphere. And then this would roll over if you got to group roles. Whenever you did an inquiry, somebody was in charge of actually collecting the resources they need. Somebody's in charge of making sure the measurements are taken accuracy. All having a different role to do so you didn't get the bossy ones that are taking over, or the lazy ones that are sitting back. And there's ways to manage and embrace the buzz. Embrace the buzz.
Embrace the buzz of science. Yeah.
Yes.
I really love the science ambassadors idea there. I can't believe I haven't thought of that before.
Well,
That's
science
brilliant.
ambassadors don't just have to be, a dog's body for resources. They can do things on the playground. If you give them an activity to do at lunchtime or break times, a science activity, they could talk to parents on open evenings or open occasions, coffee mornings and things. They can be responsible. They can do some monitoring. Children are fantastic science monitors. When you're trying to find out what's going on in classes, they are very honest. So yeah, they can do a good range of roles.
Yeah, that's really good. Yeah, you could almost appoint them in every class, and then, like you have a student council, you could have like a council of science ambassadors. I think
Yeah,
there'd be kids in every
yeah.
class that would love that role.
And it's surprising the children that apply as well. At my last school, they weren't called science ambassadors because we had a lab. So they were the lab committee. And it was year fives and sixes that were allowed to apply because they had quite a range of jobs, including writing a blog and things like that. And the children, I think, over half of them were SEND children that became the lab committee members because they just, they knew they could do science. It wasn't all about facts and writing and stuff.
Amazing. Okay. I feel like I've learned so much from our chat today. You've given us all these practical tips, um, loads of strategies to take away from the episode. And I think for me, one of the key takeaways is still to create that inquiry skills progression map and to be able to, put it in writing. What exactly do we want to do here? And then work from there as kind of a foundation, among many other takeaways. But I think if I were to just choose one, it would need to be that. It's really been an absolute pleasure to have you on the show, Tracy. And before we wrap up, do you have any final words of advice for teachers who are just looking to strengthen their students' inquiry skills?
I think I'm going to quote Anne Goldsworthy. She always says that teachers sort of dunk children into investigations and hope for this magic osmosis of skills. But there is no magic osmosis. And I think it was an Ofsted science subject report. Dr. Jasper Green said, children don't get better at drawing graphs just by drawing more graphs. You do need to teach science inquiry skills explicitly.
Brilliant. A massive thank you, Tracy, for coming on the show. It's honestly just been an absolute pleasure. So thank you so much for sharing with us today.
Thank you.
So there we have it, folks. Tracy Tyrrell has given us many, many practical ideas for helping students to build their own inquiry toolkits in the classroom, from creating a progression plan for the inquiry skills to helping teachers with the right mindset in the classroom. I hope that we're all feeling just that little bit more inspired to bring some of these strategies into our own classrooms. As always, thank you all for listening to the Primary Science Podcast. I'll see you next time for a chat with Professor Sarah Earle, who'll be giving us a bit of a masterclass into the complexities of assessing science inquiry skills. It's been an absolute pleasure. Until next time, bye-bye.